Hello everyone, welcome back to Nated Engineering once again. Today we are doing another exercise on gradually applied loads. The exercise that we are going to look at reads as follows. A member consists of three sections. The first part is a pipe with an outside diameter of 80 millimeters and is 600 millimeters long. The second section is a solid bar with a length of 200 millimeters and a diameter of 100 millimeters. The third section is a 50 millimeter square bar with a length of 500 millimeters. All the sections are of the same material and the Young's modulus is 210 gigapascal. A tension of 200 kilonewton is applied to the member and causes the total strain of 7.548 times 10 to the power negative 4. And then we go to the questions. They say calculate 4.1 the inside diameter of the pipe, calculate the total change in length, which is 4.2. 4.3 calculate the maximum stress in the member. And then we go to 4.4, which says calculate the total strain energy for the member. So this is what our diagram will look like. Always draw a diagram when you are solving your problems. So this is the diagram that we are having. They told us about an outside diameter here, which is 80 millimeters, implying that there is an inside diameter, and that is confirmed by the first question where they ask us to calculate for the inside diameter of the pipe. Therefore, the first part of this member, which we are going to say it's number 1, it's a hollow pipe with an outside diameter of 80 millimeters, and the inside diameter is unknown. We're having the length, and number 2, we're having the diameter, we're having the length. Number 3, it's a square material with a cross-sectional area of 50 millimeters by 50 millimeters, and we are also given the length. We're given the force applied to the member, we're given the modulus of elasticity, and we are also given the total strain. And then question number 1, they say calculate the inside diameter of the pipe. Copy the diagram on your screen because I am going to erase it. So we're going to start with our questions. .1. We're going to use the strain to calculate for the inside diameter, which is the total strain that is given to us. The no total strain is given by strain number 1 plus strain number 2 plus strain number 3, since we have 3 sections in this member. Therefore, we know that the formula to calculate strain is the change in length divided by the original length, or the total length. And then we are going to substitute here. Plus, this is change in length number 1, length number 1, change in length number 2, length number 2 plus change in length number 3 divided by length number 3. And then we know that x is equals to F L divided by A E. That's exactly what we're going to do. We're going to substitute our x here, and then we're going to end up with something like this. E is equals to F L A E all divided by L. This and this is going to cancel out, and then we'll be left with something like this. Our strain is equals to F divided by A E. That will be area number 1 plus F area number 2 strain plus F area number 3 strain. Therefore, we are going to take the force and strain as a common factor, since they are the same throughout. Strain will end up with a formula like this: 1 divided by area number 1 plus 1 divided by area number 2 plus 1 divided by area number 3. This equates to what? The total strain. We are looking for the diameter, the minimum diameter of section number 1. Therefore, we are going to make the area, which is area number 1, the subject of the formula. So let's do this. We no longer need this. So let's make area number 1 the subject of the formula. Area number 1 will be given to us as total strain times the Young's modulus divided by what? By the force in bracket minus 1 over area number 2 minus 1 over area number 3. And then we are going to substitute from here. What is our total strain? Our total strain is given to us as 7.548 times 10 to the power negative 4 times our Young's modulus, which is 210 times 10 to the power 9, divided by our force. What is the magnitude of our force? Our force is 200 times 10 to the power 3 in brackets. Let's erase this, don't need it. Minus 1 divided by area number 2, which will be pi, divided by 4, I'm going to put the 4 here, times 0.1, that will be squared, minus, let's put a bracket here, in bracket, remember the last part, it's a square, therefore we're going to say 1 divided by 0.05 times 0.05. And obviously, after getting our answer here, remember the answer that we are going to get, this is not equated to area number 1. Therefore, we have to bring the area, we may have to make this the subject of the formula basically. So we have to do this here. All raised to minus 1. So that's what we are going to do. After getting the answer here, we are going to say to the power minus 1. Therefore, our area, which is area number 1, will now be given to us as 3.771 times 10 to the power negative 3. And then from here, we can now calculate for what they asked us to calculate, which is the diameter, the small diameter or outside diameter. Area number 1, it's equals to what? D squared minus, actually it's, let's say pi, it will be pi divided by 4 in bracket D squared minus the inside diameter, which we are going to represent it as a small letter d. And then from here, what are we looking for? We're looking for this, so we are going to make it the subject of the formula. We're going to end up with something like this. D is equals to the square root of D squared minus area times 4 divided by pi. Then what is the diameter of the outside? What's the outside diameter? It's 0.08 squared minus our area. We got it as 3.771 times 10 to the power negative 3 divided by times 4. Forgot the 4 divided by pi. And then from here I got that our D, small letter d, is equals to what? 0.04 milli. It's meters. And that is our answer. We then go to question 4.2, which says calculate the total change in length. 4.2. Total change in length is given by change in length number 1 plus change in length number 2 plus change in length number 3, since we have 3 sections. The formula for change in length is equals to force length divided by area modulus of elasticity. Therefore, we're going to substitute here. Force area number 1, length number 1 rather, area number 1 modulus of elasticity. Length number 2 divided by area number 2 times modulus of elasticity plus force length number 3 divided by area number 3 times modulus of elasticity. And then we are going to say the force and the modulus of elasticity are common throughout, therefore we're going to take them as common factors. In bracket, it's going to be length number 1 divided by area number 1 plus length number 2 divided by area number 2 plus length number 3 divided by area number 3, close bracket. And then from here we are going to substitute. Our force is 200 times 10 to the power 3 because it's kilo. And then our modulus of elasticity is 210 times 10 to the power 9. That's giga. Open bracket. Length number 1, 0.6. Divided by area, I'm going to put the 4 here. And our area is pi times 0.08 squared minus 0.04 squared. Remember here we're dealing with a what? A hollow object. Plus, I'm going to put our length number 2, which is 0.2. I'm going to put the 4 here. Pi times 0.1 squared plus length number 3, which is 0.5. What is our area? Remember here we're dealing with a square object, a object with a square cross-sectional area, which is a 50 millimeters by 50 millimeters, 0.05. Close the bracket. And then from here we are going to get our answer as, delete this, move this up. We're going to get our answer for the total change in length as 0.366 times 10 to the power negative 3 meters. Or you can just write it as 0.366 366 millimeters. That's the same thing. And then we move to the next question, which is 4.3. And they say, calculate for the maximum stress in the member. Where will the maximum stress occur? In which section will the maximum stress occur? We know that the maximum stress will occur in the section with the least or the smallest cross-sectional area. 4.3. Remember, we did calculate for the cross-sectional area of the hollow pipe, which is section number 1, and we got that the area is equals to 3.711 times 10 to the power negative 3. The next area that we're going to look is the 0.05 times 0.05, which is the last object. And here we are going to get 2.5 times 10 negative 3. It's cubic, is meter squared. Therefore, we have our section with the smaller cross-sectional area. Therefore, we're going to say maximum stress is given by force divided by area, which will be 200 times 10 to the power 3. And here will be 0. Let's just put the area because we know it. Times 10 to the power negative 3. This will give us our maximum stress in the member is 80 megapascal. And that is our maximum stress. We go to question number 4.4. They say calculate the total strain energy for the member. Erase this. .4 strain energy is equals to half F change in T. Half, what is the force? 200 times 10 to the power 3 times what is the total change in length? Just calculated 0.366 times 10 to the power negative 3. And then what is our strain energy? I got that it is 36.6 joules. And this is how we go about answering this question. I will see you on the next lesson.